A vessel contains 1 ton of a liquid with a specific heat capacity of 4 kilojoules per kilograms Kelvin. The vessel is heated by a steam at 393, which is fed to a coil immersed in an agitated liquid, and heat is lost to the surroundings at 293 Kelvin from the outside of the vessel. The surface area of the coil is 0.5 meters squared, and the overall heat transfer coefficient may be taken as 600. The outside area of the vessel is 6 meters squared, and the heat transfer coefficient may be taken as 10. So what do we have here? What is our situation? Well, we have this liquid, and we don't really know what this liquid is. It resembles water because its heating capacity is similar to the one of water, but it doesn't say it's water. We can take it to be water just for simplicity, but it doesn't really say that's water. And there's 1 ton inside this vessel. So we have this little vessel here. And then the way that I thought about this is I drew this little coil. So this blue guy here is a coil. That'll be the coil. And the way that I thought is exactly the same way of our lab experiment, right? If you guys recall, our lab experiment, we had the shell and tube equipment, and we had a little vessel that was heating up the water so that we could have our hot input. And inside that vessel, there was this little this coil, this metallic coil that heated up, and then drew exactly the same thing. And then I know this coil is passing steam at 393, and this steam is leaving the coil and going into my fluid. But at the same time, I also have T infinity. And because T infinity is at 293, then this fluid is also losing energy to the environment. Right? So if we simplify this problem and we remove this part of the problem, then the temperature is going to increase until both have the same temperature, until both have 393, right? That's the idea, because we're going to have putting more and more energy into this fluid all the way until it reaches that temperature. However, since we have this other guy there, the more this temperature increases, the more the delta T between the fluid and R2 infinity will be, and therefore more this guy here will be increasing, right, as this guy is decreasing. So our tendency is that our dt, let's write like that, our dt, that is how my temperature is varying with my time, it should start as a big number and decrease over time as my temperature is greater and greater to my Q out is greater and greater, and my Q in is smaller and smaller. Okay, cool. So what are we to do now that we have that set up? We are to find how long it takes for this to heat this liquid from 293, which, mind you, is the temperature of the outside. So they were both at the same temperature before the whole thing began, to 353. And what is the maximum temperature to which a liquid can be heated? So there's two-part question. What is the maximum temperature, and what is the time it takes? Okay, and like I said, if we didn't have this left part of the problem, then what's the maximum temperature we could reach? Well, 393, right? But since we have that guy there, there will be an equilibrium point that we can find. How are we going to solve this? We're going to solve this the following way. What I'm going to do is I'm going to strip this down into only our control volume. So I'm going to draw this again here, like so. So I'm not drawing the coil, I'm not drawing the vessel, I'm not drawing anything. I'm just drawing the fluid in question. And that is our control volume. We're interested to know what's happening with that guy. And the most fundamental thing that's happening, if you do a little energy balance, right? We have Q in and Q out. Q in and Q out. Okay? They both happen to be convective, and we happen to know how to calculate convective heat, right? So that is the fundamental energy balance happening in our fluid. Now, I'm going to do two different equations to this. I'm going to apply two different equations to this little isolated system. So this is my isolated system. Or if it's actually a better way to do it, right, this is our control volume. Okay, the first thing I'm going to say is I'm going to remind you guys of our lumped system analysis. If you guys remember our lumped system analysis, the lumped system analysis said the following: the heat, the energy, transfer into the body in a time dt. So heat transfer into or out of, right? Into the body in a certain dt has to be equal to the change in energy of the body in dt. So it's a fairly obvious sentence, but that's what we're doing. So what I'm saying is, if my Q in is greater than my Q out, then the energy of this body will increase. If, on the other hand, Q out is greater than Q in, then the energy of this body will decrease. That's what the lumped system analysis is saying, right? And it's all changing together. So the way that we write this is, okay, what is the heat transfer that's happening in this case? And what's the left-hand side? Well, it's convection, right? We only have convection taking place. We only have convection taking place. And what is the change in energy of the body? Well, we know how to calculate that, right? Because we know the change in energy of the body is how the mass, C sub P, and delta T or T is changing with time, right? So changing with time. Now, the way you guys are used to seeing this is strip this down and we have it like that, right? That's the way you're used to seeing this. But remember that in the first class, I've told you guys why we were only considering that guy there, because our T was constant. Our T would not change. Our temperature of the wall would not change. The temperature of the two bodies interacting would be a constant temperature. So that's why we could take out a derivative. This is not the case now, right? At this point, our mass is constant. There's no mass flow. There's no water or liquid going into or out of this vessel. So in reality, what happens is that this mass can leave the derivative, and our C sub P can leave the derivative, but our temperature cannot. Okay, so as a matter of fact, what I'm going to do is exactly that. Do this. So in our case here, for our analysis, what happens is we have mass times C sub P, and then we have how temperature is varying with time. This has been derived for in your lectures, and you guys saw how to approach this. We actually, instead of having mass, we used density times volume and all of that, and we had a final equation for this situation here. But what does change is on the left-hand side, because on the left-hand side, we don't have simply our one convection, because we have two guys happening now. So what are the two convections that we have happening? Well, we have Q in and Q out. So my Q convection, and that is the second analysis I need to do, is in reality my Q that's going in minus my Q that's going out, right? And we know Newton's law of cooling that says, it's a simple equation, it says that the convection is my convective coefficient, the area through which they can exchange heat, and the delta T. We knew this already. So that means that I can rewrite that equation, my Q convection, as, what is my Q in? Well, my Q in is my H in, and that's H from steam, if you guys recall. The area of the coil for steam as well, and then the delta T for steam, minus the one for the surroundings, so infinity, area for infinity, and dt for infinity. We can write this one more time, actually, because we know those delta T's, right? So for steam, and then what is a delta T here? Well, the steam is giving energy to the liquid, right? So that's going to mean that the steam has a higher temperature. It's going to be T steam minus T fluid. And I'm going to do water here for convenience of us understanding the problem better, okay? It's not necessarily water, but I think it's going to be easier for us to visualize this as water. And on this side here, well, now the water is hotter than the surroundings, so it's going to be T water minus, getting rid of this, minus T infinity. Okay, so hit me up if you get lost. But so far, we only put down the basic equations for this. And now what I'm going to do is, obviously, I'm going to combine the two, right? Because I know what is my convective energies that I have going in and out of the body, and I know that whatever is happening has to be changing the energy inside of my body. So let's combine these equations. We're going to have my H of steam, area of steam. I'm going to go ahead and put my values there, and I know my values because I know the temperature of steam. It's a constant temperature, and it's 393. So 393 minus T water minus HA, area for infinity, T of water that I don't know, it's my unknown, and my T infinity, which I do know as well. And this has to be equal to mass C sub P and the way that my temperature is varying with time. Cool. What is next? Well, we have this and we have this, so we can plug those guys in. Let's do that. So actually, we have all of these. We have this, 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 and this. So I'll plug all of them. So my one for this steam is 600. The area of the coil is 0.5. This guy is 393 minus T water. This fella here is 10. The area is 6 meters squared. T water, 293. And then this is a ton, so that's 10 to the third kilogram. And the C sub P, this is where I went wrong, is 4,000, right, joules, not 4 joules, 4,000 joules per kilograms Kelvin. And dt. Okay, so now we have some numbers. And I can simplify this, so what I'm going to do is I'm going to multiply here, I'm going to multiply here, and I end up with, and then I can sum up these guys here, or subtract them according to math, and I end up with this, 13, 440 minus 360 T H2O equals 4 times 10 to the 6 dt. Okay, what is this? This is the general equation that explains our problem. Let's actually write that down. This is the general equation that explains this problem. So what is this? This is saying, this is telling us how the temperature of our fluid inside the vessel is changing in relationship with time. And it's taking into account the amount of fluid that we have inside and the two energy transfers that are happening, two convections that are happening. Okay. Now, what do we need to do? We need to find two things. We need to find what is the maximum temperature that this fella can reach, and we also need to find what's the time it's going to take for it to go from 293 to 353. Okay, I'm going to start with how far it can go because I think this is easier from the point we are where we stand. Check out what's going to happen. Remember what's going to happen. We have let's try to do a graph to make it easier for us to understand. On this axis here, I'm going to put this guy, and on this axis here, I'm going to put time. Okay, what is happening? Let's go back to our drawing. What is happening? In the beginning, before anything starts, this is 293 Kelvin. This is 293 Kelvin. This is 393 Kelvin. Right? So in the beginning, our delta T over here, this delta T over here, stupid. My delta T over here is greater than my delta T over here. As a matter of fact, there's no delta T over here. There's no Q out in the beginning. So I only have energy going in. But as this number starts to increase, right? Let's say I have now 340, okay? Now I have delta T over here, and I have a delta T over here. And the bigger this number gets, the bigger this delta T gets, so the bigger this Q gets, and the smaller this Q gets. So at some point, we will reach something called equilibrium. What is equilibrium? Well, equilibrium is precisely the point in which my two energies are exactly the same. What does that mean? It means that my Q, at some point, my Q out equals my Q in. And when that happens, my temperature won't change anymore, right? Because all the energy that is coming from the steam is going away to the surroundings. So I can't have this fluid change temperature anymore. It's just going to be stuck on that equilibrium temperature. So what does that mean? And let me get rid of these mock temperatures that we drew. I can't. That's good. Okay. So what does that mean? Well, let's think about for a moment. How is this temperature changing? How is the temperature of our fluid changing as time elapses? Well, in the beginning, there's no Q out, so we have a big temperature change, right? It's going to increase fast because our delta T in relationship to the steam is high. So our dt will be somewhere on the top there. Let's actually use different colors so that this is makes more sense. And then the way the temperature change with time is going to decrease ever more to the point in which it becomes zero. Why does it become zero? Because the temperature cannot change anymore, right? So it doesn't matter how much time elapses, it doesn't matter how much time the guy stays there, whatever energy the steam is giving is going away to the surroundings. It's just going to stay there stuck. So how is that going to vary? Well, it's going to vary like this, right? It's going to go downwards, 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 until it reaches zero and then just stays there. And at this point here, we have reached equilibrium, right? So in other words, at dt equals zero, I have equilibrium. So what I can do is that in my general equation, I can say dt equals zero and then find what's the temperature, because that temperature there that we find when we do that, using the dt equals zero as our control, as our boundary condition, is the equilibrium temperature, and it cannot rise more than that. So it's going to stay like that. So let's see, maximum T is at, or when, is at dt equals zero, right? So what I'm going to do is simply I have this minus this equals 4 times 10 to the 6 dt, and I'm going to say this equals zero. Okay, so I'm going to do this equals zero. So no, my only unknown is going to be my temperature, and therefore my temperature will be simply this number divided by this number here. And that is 376.3 Kelvin. Okay, so this is the maximum temperature we can obtain. One quick question, why is it Kelvin? Because we've plugged these numbers here as Kelvin, right? Right in the beginning there. If we were to plug those guys as Celsius, they would be Celsius. Cool beans. So we have knocked down one of the parts of this question. Now, next part, how long does it take? So how long to go from our initial 293, was it? See the question? Yeah, 293 to, what is the end goal here? 353. Well, we know the equation that explains that, right? That's our general equation. So 13,548 minus 360 T H2O equals 4 times 10 to the 6 T dt. So all I have to do is I need to integrate this bit here in respect to time and integrate this bit here in respect to temperature, and I can find the temperature, right? Now, there is one extra step to make your life easier. I didn't do this step when I was solving it by myself, but I'm going to do it with you guys because it makes the math easier, which is to divide everything on both sides by 360. Okay, so that way we can eliminate this fella here, and then this number is going to be smaller, this number will be smaller. When we do that, this equation becomes 376.3 minus the temperature of our fluid. This is 11,111. Okay, what I'm going to do, I'm going to send dt multiplying to that. So I'm going to send this guy multiplying over there, and I'm going to send this whole term here dividing for that side. So I'm going to have on one side simply dt, which is convenient because I'm looking for my time. And the other side I have 1, 1, 1, 1, 1. Differential for temperature divided by 376.3 minus my temperature at any given moment for this fluid. What do I do next? Well, I integrate. And I want to integrate this guy in respect to from when time starts to the time that we don't know. And I want to integrate this guy here. The temperature goes from 293 all the way to 353. Okay, I won't go into the details of the integration now, but I can do it later if you have trouble. But what you need to do is substitution, right? If you guys recall, I'll quickly how you do it. You do U equals 373.3 minus T, and then you do du dt, which equals minus 1, so therefore du equals minus dt, and then you can solve using substitution as a simple integral. So what is it this turns out to be? This turns out to be T on this side here, from 0 to T, and on this side here we get 1, 1, 1, 1, 1, because this can leave the integral, and I'm going to get minus natural log of 376.3 minus TH2O, and we're going from 293 to 353. Okay, this negative here comes to be because of this negative one. Can sub in the values. Natural log of two difference there, so 83.3 divided by 23.3, 14.155 seconds. Let's do some conversion quickly. So divided by 60, divided by 60, so this is roughly 4 hours. So it takes roughly 4 hours under the conditions that were presented to us for this guy to go from 293 to 353. And we also know that this is possible, right? We know that it's possible because it wouldn't be possible if it were asking us, how long does it take for it to get to a temperature of 380, for instance, 380 Kelvin? Well, that wouldn't be possible because we know the maximum temperature it can reach is 376. Since 353 is smaller than 376, all good. So that does it for the first part of the question. So now we can tackle the second part. Okay, part 2 says the following. When the liquid temperature reached 353, the steam supply is turned off for 2 hours and the vessel cools. So let's actually look at what we're reading. Okay, so once the temperature reached the 353, after those about 4 hours have elapsed, then the steam supply is turned off for 2 hours and the vessel cools. So pretty much what this is saying is that this guy goes away, right? Instead of having both Qs, one Q in, one Q out, we instead only have Q out. How long will it take to reheat the material to 353? So the thing that's being asked is the following. Okay, we still have the situation here, but then suddenly we remove this guy here for 2 hours. 2 hours lapses. Then we turn this guy on again, and it's asking us how long will it take till it goes back to those 353. So the question really, it's a two-part question, right? Because the first thing is, what is the temperature T after 2 hours? And once we find what's the T, then the question is how long, what's the time from this T that we just found back to 353? So it's a two-part question. So let's do that. First thing we need to find out, what is the temperature after this time elapses. So let's go, let's go to the side here. Let's tackle part 2. And the first thing I want you guys to note is that literally what's happening is when we turn it off, we're removing this Q, right? And then we're left only with that situation there. And what does this mean mathematically? Well, I'm actually going to copy it, and we're going to use exactly the same thing once again, because remember how the whole thing came to be. So we came up with this equation here. I'm going to copy this. Now I learn how to copy. We have that situation there, but now this fella goes away, right? Because our steam is turned off. So our equation for this, we're left with only HA area, temperature minus 293, which is the temperature of the surroundings, mass Cp, dt. So it's a simpler equation, right? And we have the values for it, so we can solve for that. And using this equation that we're coming up with, we can find what is the temperature. So know how this is going to be simplified, right? So we have minus 60 here times T. I want to leave it as multiplying. Sorry. On this side, we still have the same 4 times 10 to the 6, right? dt. And this is the general equation for case 2. So let's do general equation, case 2. All right. Now, what is the question? What will be the temperature after 2 hours have elapsed? So after 2 hours have elapsed, what's the temperature? Well, this is the time component here, so we have to integrate it from 0 to 2 hours. We need to remember that this is in seconds, so it's going to be 2 hours times 3,600 seconds. And our temperature is starting at 353, and it's going all the way to something that we don't know. So quite literally, we have to do the same thing we did before, which is I'll send dt to this side here, and I'll have 4 times 10 to the 6, the temperature divided by minus 60, TH2O, 293. Okay, once again, we can integrate on both sides. On this side here, I'm going from 0 to 2 times 3,600 seconds. And on this side here, I'm going from 353, which is the temperature when our power is cut off, all the way to a temperature that I don't know, which is what I'm interested in. Once again, I can remove so on this side, I'll just have 2 times 3,600 equals, once again, these guys here are constants, right? So I can remove them from the integral, so it's going to be negative 4 times 10 to the, let's just keep it, make it simple. Let's just do 5 over 6. We can just leave it like that. And we're integrating from 353 all the way to t, dt over temperature minus 393. Once again, substitution is the key here. Like I said, if you guys want, we can do that later when we finish this problem. Okay, but basically, natural log of C2H2O minus 293. This case here, there's no negative because it's not 393 minus temperature, it's the other way around. We're integrating from 353 all the way to T. So that means that I'm going to send these guys, I'm going to send this guy multiplying, this guy is dividing, this is going to be minus 0.108 equals natural log of T minus 393 minus natural log of 353 minus 293. Okay, this is just a subtraction of two natural logs. It's just natural log dividing the parentheses inside. So that should be over 60, right? So what I can do now is take the exponential on both sides. So take e to the minus that, and then I'm going to remove that. So it's going to be left with temperature minus 393 divided by 60. And therefore my temperature equals about 346.86 kelvins. Okay, this is not our answer, right? But this is part of what we need to be able to solve it, which is after I remove that steam, that energy, the input energy, for 2 hours, how much will this temperature decrease? Well, it will decrease from 353 all the way down to 356. So it's not that much of a decrease if you think about it, right? So this is because the convective coefficient on the surroundings is not that big. So losing about what? Less than 10 Kelvin, right? And now the question becomes, okay, so now that I'm at 346, how long until this temperature can grow again to the temperature, the original one, the 353? And then for this last part done, we just apply what we know, right? Because then let's do this like this. Okay. How long will it take to go back to the 353? Well, if we're turning on the steam again, then we go back to this, right? We go back to this general equation here. So what we need to do is plug this guy, and then we integrate the dt for temperature from 346 to 353, and we integrate our time from 0 to t and find what we're looking for. As a matter of fact, what I'm going to do is I'm going to plug this one here, because it's a simpler version of it. Okay, so let's go ahead and do that. So 376.3 minus the temperature we're looking for equals 11111 dt dt. So dt equals 11111 dt divided by 376.3 minus h0. Obviously, when you do this on an exam, you're not going to do all these steps again. You're just going to grab directly this, right? You can plug in directly this because everything else is going to be the same. But since we're doing this step by step, I'm going to go ahead and integrate this fella here, and we're going to integrate this from 0 to the time we're looking for, and this guy here from 343.86 to 353. On the left side, we have the time. On the right side, we're going to have this multiplying my natural log of negative natural log. Okay, so now the only unknown that we have in this problem is actually the time. So easy peasy, right? This turns out to be 2598.87. And don't forget this is in seconds. So this is time that it takes to go back. And we can convert this, so this is roughly can actually approximate these. 2600 would be a good enough answer, right? It's 2600 seconds, which is roughly 0.7 hours or so. Okay, less than an hour, 0.7 hours. So remember that it took us 4 hours to go from room temperature all the way up to 353. Then we left it for 2 hours and it only dropped about less than 10 Kelvin. So now that we want to turn on the whole system again and let it increase the temperature, it's going to take us less than 1 hour to get there. Okay, so it's consistent with the whole system that we have going on. Do you have questions?